IRTF Open. So my name is Dirk Kutscher. I'm the new IETF chair, and next to me, I guess you still know Colin, the outgoing IETF chair. And let's just start the meeting. And okay, it's a bit slow. Okay, so just some housekeeping rules. So please note that we are operating under the IRTF IPR policy, which follows the IETF rules mostly. So in short, that means if you contribute IPR related matters or you're aware of contributions, you are expected to notify us shortly. And please note that we are taking audio and video recordings, and this meeting is also live streamed. We have a code of conduct, a privacy code of conduct. Please make yourself familiar with it. And we also have anti-harassment procedures, so IRC 776, which also apply to the IRTF.
Dirk, can you speak a little closer to the mic?
Okay. And yeah, so it's Thursday. I think you are familiar with the Meet Echo system. Please use the client and sign up if you attend this meeting here. And use the queue management system later if you want to ask questions. So we are the Internet Research Task Force. We are not setting standards. We are doing research. And sometimes it's confusing because we are like in the same location, same time. We use sometimes similar procedures or mechanisms, but just be very aware that we're not doing standards here. Okay, so the IRTF has a set of really interesting research groups. So the ones in light blue have already met this week. The dark blue ones are still going to meet tomorrow, so HRPC and ANRP. If you have time, please attend those meetings. And the gray ones didn't meet this week. Okay, so we started a new research group on sustainability and the internet. So the group is called Sustain. That had its first meeting earlier this week. And Ali is later going to give us a summary of that meeting and will tell us more about what this group is going to do, how you can get engaged, and so on. Okay, so we just very recently published IRC 9775. That's the IRTF Code of Conduct. So it's describing how we want to do effective research in this environment, and also refers to the same anti-harassment policy, ombuds team settings, language guidelines, and so on that we use in the IETF. So, so Colin was driving this. Thanks very much. And so the ISG at large also helped a lot in moving this document forward. Okay, so so we are really glad that we have support by Akamai, Comcast, Google, and Netflix for our diversity travel grants. So we are, for each meeting, we are offering travel grants to for early career academics and PhD students from underrepresented groups, so to enable them to attend our meetings. And so for the next meeting, the IETF 123 in Madrid. Please note that the deadline for applications is March 21. So Right, so you have one day if you are interested. So we have to do this because it takes a lot of time to get visas these days. So and we want to kind of make it really possible for people to attend if they get these grants. Okay, and so the IRTF is each year is organizing the Applied Networking Research Workshop, ANRW. And this will be co-located with the IETF 123 in Madrid in the summer. So the format is that we have a full day during the IETF week with interesting presentations and discussions. So this year's ANRW is organized by Anna Brunström and Ryan Beckett. So they are the TPC chairs. And yeah, you can still submit your papers. The deadline is April 15th. And yeah, we also have the Applied Networking Research Prize, ANRP. And so the ANRP tries to identify really good work in so academic conferences, for example, that have relevance to the work in the IRTF and then also by extension IETF, so work that helps moving the internet forward and has been recognized by good conferences. And so you can nominate work that you see there, and then there's a committee that selects the best work, and then we have the pleasure of inviting authors to present their work here. So the ANRP is also kindly supported by the Internet Society, Comcast, and NBC Universal. Thanks very much. That makes it possible for us to award these prizes. And so this year we had a very good award committee again. So thanks to everybody who helped in the selection process. So we had received 69 nominations and had made 6 awards out of those. Yeah, and it's our pleasure to announce the winners for this IETF. And so we have 2 talks today. And so congratulations to Zhangye Wang for his work on the use of large language models to support network configuration, and to Henry Birch Lee for his work on secure collaborative path control in BGP. So we are going to hear the talks shortly. And just let me quickly show the agenda. So yeah, we hear Zhangye's talk first, and then Henry's, and then after that, Ali is going to give us the summary of the Sustain meeting. Are there any other suggestions for the agenda? Okay, then I suggest we start with Zhangye's talk, and you wanted to share your screen. Okay? Yeah, here's a click. Kind of sluggish today. Oh, okay. If you click it, right? It takes some time. Wie geht's denn? Ernste? Okay, so it's not? Okay. Yeah, so somehow our network is a bit slow today. So the paper title is NetConf Eval, Can LMNs Facilitate Network Configuration? And the authors are Zhangye Wang, Mariano Scasariello, Aliesa Fashion, Simone Ferlin, Dejan Kostic, and Marco Chiesa. And Zhangye, you have the floor.
Closer. Hello. This is Zhangye Wang, second year PhD student at KTH. So today I'm going to introduce our recent work, NetConf Eval, Can large language model facilitate network configurations? This is joint work with Mariano, Aliesa, Simone, Dan, and Marco, as mentioned before. And as far as we know, orchestrating network is always a cumbersome task. And as a network operator, they need to configure the network carefully and manually to ensure the reliable transmission of data. And they need to learn large. This is slow. They need to learn large software documentation to get started with the work. They need to learn how to detect and debug complex network or application value, which happens a lot in the network. They also need to learn how to deal with cyber attacks or vulnerabilities. There might also be some misunderstanding within their own development team, which could result in network misconfiguration. Therefore, manually configuration is always costly, difficult, and susceptible to human error. Animation doesn't work well, but I have a lot of animation to talk. But even minor error could result in a serious disaster, like a flight disrupt at Amadeus and an outage at Meta. Some network synthesizers has been developed to solve the problem, and they aim to generate some low-level network configuration from human intents. For example, Propan, CNET, and Contra here. And however, the problem with these tools is that the abstraction of network always require these tools to employ a self-defined specification or language to describe the network intents. For example, CNET here, they will use a stratified deadlock to express the language. This, of course, poses challenges to the network operators because they need to learn this domain-specific language to get started with the work, and it's also hard to extend the use of these network synthesizers because they need to understand the inner mechanism of a whole system by understanding all the stratified deadlock. And if they want to implement a extra function in the network synthesizer, they should learn how to write it in stratified deadlock as well. This makes us to think that whether there exists a tool that can directly understand what the network operators want and do the whole configuration for them. And this is what we might get from LM. And typically, a large model will take some input, task, express in human language, and output it in text, code, script, and also configuration could be. This sounds like a perfect fit for this case, but before we move forward, we can first take a look at what are large models. Typically, LM is made of huge neural networks trained on large corpus text, and once given text input, they will try to predict the next sequence of words, which result in a full sentence, full paragraph, or even full documentation. Typical LM these days are ChatGPT from OpenAI, Cloud from ANRP, and Llama from Meta, and we also have much more advanced model now using some techniques like MOE. For example, there's also DeepSeek. And these days are able to generate coherent, contextual relevant text based on the prompts, and they have been proven to be knowledgeable, to be a fast learner, and to be creative. Based on all the advantages, we really start to think that whether we can have an idea that in an ideal case, we can have a network operator directly talk. This animation. In ideal case, we want to have a network operator directly talk with the LLMs, and LLM will do all the cumbersome tasks we have mentioned before by configuring the network. However, opportunities always come with challenges, and I think you have already know a lot of problems with the LLMs. For example, the first one is unreliability, because the answer generated by LLM could always be wrong, and if we put the wrong answer in a network, this, as we mentioned before, it will.
One moment. We just switched you to Ethernet because it's too slow. Can we try to reshare it?
Stop sharing.
Yeah, try to reshare. Yeah. Sorry about that. Okay. It may work better now. Okay, thanks.
Yeah. The biggest question first is unreliability, because the answer could be wrong, and if we put the wrong configuration, wrong answer in the network, it results in disaster, as we mentioned before. And the second thing is about the cost. And according to the data here, to train a GPT-4 level large model from scratch, we want to spend more than $50 million. And as model size increase a lot these days, the largest model has already reached trillion number of tokens. How to deploy this model is also a question, because we need to buy extra GPU devices and allocate them. Okay, what we do in our work, we try to assess large models into this networking task. And we have designed a set of benchmark, which is called NetConf, to evaluate LM for networking. And we formulated a few takeaways based on the experiments with the benchmark to share our experience. And we also present a prototype for large model-based networking system, just to show it's really feasible to build some system with LM involved. And in this paper, we mainly focus on 3 tasks. The first task is to translate the human language input, which is high-level requirements from network operators, into a formal specification format, which could be a well-structured format rather than a human language, which is a bit chaotic. And second task is to adapting code to new requirements, which means, for example, we can write some code that we can install in the network control plan. And the third task is to generate some low-level network configuration, for example, BGP, OSPF, or even P4. Let's look at the first task, the translation from high-level requirements to a formal specification format. And imagine the network operator now wants to direct traffic from RAM to Milan to traverse a firewall. And when we have a network, human language input, it's almost impossible to process it with other tools like CNET or the network synthesizers we have mentioned before. So it's important to put in a well-structured format. So LM task in this task is to translate a natural language input into a dictionary or other well-structured format. For example, here we have reachability from RAM to Milan, waypoint from RAM to Milan to 501 or 502. And to evaluate how LM is good at this task, what we do, we try to generate a few 3,200 requirements, focusing on reachability, waypoint, and load balancing using config to spec, and which is a tool to convert network configuration to some specification. But here the specification is still in a well-structured format. So what we need to do now, we first pick a certain number of requirements, slice them into batches, and for each batch, we try to convert the specification into natural language using a predefined template. So in that case, we can have a natural language input, and we can feed the natural language input back to LM again, just to test the capability of the translation from a natural language to a specification. And here is the performance of GPT-4. Actually, GPT-4 can translate accurately the requirements. The x-axis here is the number of requirements per batch, and the y-axis here is accuracy. And we can see GPT-4 can get almost 100% accuracy before the number of requirements per batch, which is turning. Of course, the performance comes with a cost, and here is a cost per request. But it's worth mentioning that the cost per request is decreasing when we increase the number of requirements in per batch, because for one single batch, a large amount of requirements share the same context, which reduce overhead. GPT-4 is typically a really large size LLMs, and there are some typical issues with this large size large language model. They usually have more than 1,000 billion parameters with really slow inference time, and it's resource intensive, which make them hard to deploy for like research units like our university. So we start to think about whether we can use some small or medium-sized models, which typically have 1 to 1 billion parameters with fast inference time, and then easily can be deployed on a few set of GPUs or even on a laptop. So, but how do smaller models perform though? We tried experiments with GPT-4, which is a smaller size model than GPT. We tried the experiment with GPT 3.5, which is a smaller model than GPT-4. And actually, we can see smaller model, of course, performs worse. But luckily, we got even improvement in the cost but this is due to the billing system of OpenAI itself. And GPT 3.5 is generally cheaper than GPT-4. We can tell it from the model size, and GPT 3.5 has a much smaller model size than GPT-4 itself. But it's worth mentioning that with the number of requirements per batch is less than 5, and we can still reach almost 100% accuracy, but with the much lower cost than GPT-4. And both GPT-4 and GPT 3.5, these models serve as general purpose model. What do I mean by general purpose model? And they has been trained on large corpus of text, which people can find online almost, and they are supposed to know almost everything, but they may fail in some specific tasks. For example, there's a very typical example that people find bugs of GPT-4. People start to ask how many R's is in the phrase network extraction, and the answer should be 3. But GPT-4 at that time, which was the smartest model at that time, can give you the wrong answer, which is 1. This makes us to think that whether we can find a specialized model can be expert in one specific task. Instead of doing some, like asking some random questions, reply to some random question, it only need to do the translation from a natural language to a formal specification. To get this model, one can try to first pre-train on some specific task from scratch, a model from scratch, and using a large amount of data. Or one can try to fine-tune from a general purpose model which has already been pre-trained, but using a smaller amount of data. And due to the limitation number of data we have, we only try with fine-tuning. How does fine-tuning improve the performance though? Here there's a called Llama 13B, which is a even much smaller model than GPT 3.5. But what if we have an even smaller model, for example, called Llama 7 billion, but we fine-tune it with QLoRa, which is a tool for fine-tuning, and we fine-tune it with a few set of data set. And we can see from the figure that code Llama 7B the fine-tuned version has already have even similar or even better performance of code Llama 13B, which means fine-tuning make up the gap of 6 billion parameters. We also tried the experiments, fine-tuning GPT 3.5, and it can also make the GPT 3.5 have a similar close performance with GPT-4. And it's worth mentioning now, these days, a lot of models start to support function calling, API function calling. And what do I mean by function calling? It's that LM will try to translate a natural language input into call to a function or multiple calls to a function. So OpenAI started to support the single function call from June 2023, and multiple function, parallel function call, which is whenever I have a single natural language input, it will try to output the multiple functions at the same time, and they start to support it from November 2023. So back to our question, we want to translate natural language input in a well-structured format, a dictionary. What if we predefine some functions in the backend? For example, add reachability, add waypoint, and each of the function will just, when we call it, it will just insert entry in the dictionary, or it could also do some extra functions in the real network. But now LM's task becomes to translate the natural language input into multiple function calls at the same time. So we only tried experiments with GPT-4 because the GPT-4 was the only model that supported multiple function calls at that time. And compared with dictionary, function call is less compact, but there's no need to reordering the natural language input. And how does it perform? We can see from this figure that GPT-4 start with the previous dictionary, the structure is start to degrade, the performance degrading when the number of requirements reach 20 or make it get close to 100. But when we have GPT-3.5 with function calling, it can have a much better performance than the original GPT-4, not to mention GPT-4 with function calling, with almost 100% accuracy when the number of requirements go closer to 400. This actually shows that LM is really good at one-to-one directly translation. However, to use function call, it's always an extra work to write some function to be called in the backend. So this sounds like an extra burden. Okay, that's all with the first task. Then we can move to our second task, which is adapting code to the requirements. Developing modern software is always difficult and expensive. It is difficult because one needs to adapt to the fast or rapid technical changes, and one needs to satisfy some high performance, resilience, or security guarantee. And it is expensive because one needs to hire experts with a understanding of system, protocols, and the process itself is time consuming and cumbersome. So assuming now a network operator wants to write a function, take input of something, for example, topology and network requirements, and produce a waypoint passes as the output. So now LM task is just to write code to implement this function. And to see how LM is good at this task, we customize scenario, reachability, waypoint, shortest path, and load balance. And for each of them, we just ask LM to implement a specific function, to write code to implement a specific function, to calculate the passes, satisfy requirements, including reachability, waypoint, shortest path, and load balancing. And for each of them, for each task, we also provide a few test cases for LM to test on. So whenever we got a code from LM, we'll try to input it into our test cases to test whether the code is really implemented well. So here, if it passes the test, we'll always consider it a successful run. Here we have the performance of GPT-4, and it can succeed in some steps. Oh, sorry. For example, load balance, but it fails a lot in reachability, waypoint, and shortest path. This makes us to think that where there's a way that we can improve the performance. For example, what if we provide some feedback to LM? What I mean by feedback that whenever it fails in a specific test cases, it will try. We can try to append the exact scenario of how LM failed in that case, and what is the network topology at that time, and what is the expected passes calculated, but what is the answer given by LM. And we ask LM to compare the difference and ask it to fix the code based on our feedback. And we can see feedback really improves the performance, especially in reachability and shortest path, but it still fails in waypoint. So we started thinking about, is there any extra way? What if we provide some extra help, like an algorithm help? And here is an example. We give us a super detailed, not detailed, a brief instruction of how to find the shortest path, construct the graph, identify the host pairs, find all the passes, and find the shortest one, and return the routing passes. How does this kind of algorithm help can help with the generation performance of LM? And here is the figure. GPT-4 and plus instructions plus feedback can really make a 100% success rate in almost all the cases. This even make us to think whether feedback is even necessary in this case. So we try to remove feedback, and it's still get. We try to remove feedback and still get the almost 100% accuracy. Yes. So this really makes us to think what's really impact of feedback in the performance. So here is the figure of the average number of attempts for LM to get to the correct code in different cases. And we can see sometimes GPT-4 with and without feedback, sometimes it will reduce the number of attempts to get the correct code, but sometimes it increases it. And same for the one with instructions. Sometimes it decreases and sometimes it increases. So, but we think about why adding a feedback can even make the performance worse. And our reason, our explanation is that when we append extra text to, because imagine it's not like chatting with ChatGPT, we are doing GPT-4 API, and whenever we interact with LM, and if we want to keep the communication history, conversation history, we will always append the feedback to the original text. So which means that whenever we add a feedback, it will actually add extra text to the original prompts. So the prompts just getting longer and longer, which is whenever the context is large, LM will perform worse because the large context will distract LM from solving the original problem. So therefore, the takeaway for this one is that feedback, whether to use feedback or not should really depend on the real cases, but one can try both and always find the best solution. We also tried experiments with some smaller models like Mistral, Kodayama, GPT-3.5, but none of the models that we tried at the paper submission time can generate correct code, and their error ranging from some syntax error to data structure error or even a logic error. Okay, let's move to our third task, which is generating low-level configuration. And to see how LM is good at this task, we handpick a few network scenarios from the Kasara network repository online. And here we have OSPF, OSPF multi-area, RIP, BGP, and Rift. And for the Rift one, we implemented a small factory data center network, and we handcraft FFR downlink documentation of Rift itself by ourselves, just to see how LM will behave when there's no existing knowledge about the protocol itself. So for each of the network scenario, we will try to ask LM to solve a small configuration task that can be solved by actually a few lines of code for each devices. And so once but it can only be solved by a single solution. So once we ask LM to solve the configuration problem, and once we get the answer from LM, we'll try to pass it through FFR routing. And if past FFR routing, we can try to compare the text similarity ratio between the generated configuration and expected configuration. And here the y-axis is the similarity ratio, and the numbers on top of the bar is the success runs out of 5. And we can see from the figure that if we don't provide any extra help to LM, it can still succeed in some cases like RIP and BGP with 5 out of 5 success rate actually, but which means LM already knows something, but it fails in OSPF, OSPF multi-area, and Rift. This makes us think, can we provide some help to LM? For example, what if we append the full FFR routing documentation to LM? Here, the LM we use is GPT-4 because GPT-4 is the model that can process really large context lengths by the paper submission time. And the full documentation here could be maybe 300 pages documentation. We just append the 300-page PDF with text to the original prompt and ask LM to solve the original problem. And we can see LM can actually make a better performance in the cases that it fails before, which means LM learn on the fly. But there is a value in RIP and BGP. There's a degrading of the similarity ratio. Actually, this is caused again by the context length itself, because 300 pages documentation is really large, which distract LM from solving the original problem. So how to have a better documentation? And the aim is just to make the documentation we append to the original text smaller and better. So we offer 2 solutions. The first one is index plus section, and the second one is rack. By index plus section, we first give LM the index so we ask them to pick the most relative section. And then we only append that specific section to the prompt, so which will reduce, make the documentation more concrete, and smaller. And RAG is a new technique which can divide documents into chunks of different size, and then select the most relative chunks that we can append to the context. And here we have a trunk size 9,000 based on our best practice during the experiment. But we can see, based on these, both of the solution can improve the performance by reducing the context size. But RAG here fails a little bit in the OSPF cases, but that's due to the problem that we didn't pick the most, I think, best trunk size for that specific scenario. So looking finally to Rift, which is an experiment we designed just to see how LM will behave when there's no existing knowledges. And we can see that LM can take advantage already of knowledges without even fine-tuning by just appending the text to the original prompt. And the performance increased from 0 success out of 5 from no documentation to 5 out of 5 with a really better documentation. And that's all for the experiments we have done. And based on all the experiments, we can actually come up with a few principles to build some Elm-based system for network, which could be used which could be our takeaways. So the first thing is split complex tasks into smaller subtasks, because no matter how Elm is advanced these days, it can still not solve complex tasks, and it's good to solve it, to divide the big tasks into smaller ones and solve it in a fine-grained way, step by step. And second, support task-specific verifiers, because the answer generated by LM in each step could be wrong. It's important that people to check it either manually or with some test cases, or even with formal verification. Third, keep humans still in the loop, and human can still give a lot of guidance to LM by providing some feedback, some instructions, and so on. So based on the principle, we actually have provided a few prototypes that can actually using LM in the network system. The first one is using LM with network synthesizer, and the second one is a pipeline that we built from natural language input of network intents to a low-level configuration. So imagine the first one, when we already have SYNNET here, which take input of the global requirements in a specific format, and then also the topology, and output something which is the configuration for each routers. And then the operator wants to direct the traffic from RAM to million classified as media using OSPF. And now, I mean, can LM or GPT-4 write these global requirements for network operators? Maybe no, because GPT-4 doesn't have any existing knowledge of what is SYNNET. So we can try to provide some documentation help, like the paper of SYNNET, and then LM can actually translate the natural language input into the global requirements, so make it human-friendly. And the second prototype we provide is called NetBody, which is a whole pipeline built with LM doing the tasks, doing the translation from high-level requirements to a low-level configuration. It's actually made of 3 large models sequentially. The first one is in charge of translation from the natural language to a well-structured format, a formal specification. The second one is to calculate some high-level configurations, like based on the requirements and topology, you want to try to generate some code to calculate the routing passes or forwarding tables. And the third element is just in charge of the low-level network configuration, do the conversion from the routing table to all the low-level configurations that we can install on the switches or routers. And each of them is supported by a verifier, and the verifier could, we only support in this prototype the manually check and some test cases. And we emulated this, the evaluate topology in Kasara network, Kasara emulator, and it's made of 3 hosts, H1, H2, H3, and a few switches. And how does it work? It would take input of the network topology, some physical setting, some data plan program, and also requirements in natural language from operators, and output the P4 table entries that we can directly install in the network, in the switches. So based on the first network operator's requirements, we can actually see we have 7 switches, 3 end hosts, and the switches can reach all the end hosts and route traffic from S1 to H2 to going through some waypoints S2 and S6. And actually, based on these requirements, we can know that the traffic from H1 to H2 should be directed through the blue path. And here I have a demonstration of how it should work, but I don't know whether we can.
Let's see.
Is it in voice? No.
So it's, you have to turn it off.
Yeah. The requirement from the first article.
Okay, it's also hard to,
But this is just a demonstration of how it works. Generally, it's just input something like the requirements I've mentioned before in the examples, and then I put all the input as a network requirements, and then it will go through the pipeline with 3 LMs processing each steps, and then finally install the rules in the switches. And the demonstration is just to show that by TCP DAG, we can actually track packet sending from H1 to H2 following the blue line. Okay, that's all for our netconf eval. And I also want to have a discussion of how other researchers using LM in networks. And similar to netconf eval, there is other people working on network configuration and management. And the first one from Hotness 23 is using LM to synthesize the router configuration, and then mainly focus the task of translation from one router configuration to another router, which may be from a different vendor, for example, from Cisco to Juniper. The second one is doing network management using code generation by large model, and they mainly focus on graph-based code generation to solve some specific network tasks. And instead of configuration generation, people also try to extract specification based on existing configuration. For example, this one, extract protocol specification using LM. This is helpful for network operators to understand what is happening in the network and what has been installed in the network. And at CCOM 24, there's a more systematic framework called NetLM. They try to adapting large model for networking for different specific networking tasks. More specifically, they plug a multimodal encoder at the very beginning of a large model to make LM more customized for some specific tasks like adaptive bit rate streaming and cluster job scheduling. People also try to use LM for network research, for example, reproducing network research, or even generate some network research ideas. Instead of using LM for networking, people also try to use networking for LM, because LM itself is a very large size machine learning models, and they are usually deployed in multiple devices in data center network, and during the training and the inference process, different devices with different GPUs will try to communicate with each other by exchanging some data, parameters, and this, of course, introduces a lot of communication overhead. So people in this area is trying to reducing the communication overhead by maybe increase the throughput and reduce the latency of the communication, which will also boost the performance of LM itself. And although no matter how LM is good at this other task, we are still not sure that whether LM can be used in real world scenario because of the reliable problem, as we mentioned before. And think about this case. We ask LM to, here is ChatGPT-4 actually, we ask it to write a Python code to calculate the maximum number in a set. It will actually give us a code even with some commands. It looks very good, but can we trust the code? And my answer is always no. I'm not sure what will happen if I put the code in my real system. So one can try to check whether this code is really tool is really good by providing some test units. For example, here I just provide a simple input with some example set, and I will print out the answer. Could be like 1 to 9. Now the answer should be 9. I just want to, we can just check whether the printed output is as expected. But even with the test units, can we really trust the code? Maybe not. Because, for example, in the real scenario, maybe we get the input of an integer rather than a set, and this actually will lead the code to a real value. So our next step of our research is to try to build a reliable application by formal verification. And to do so, I'll give an example here. I ask, instead of ask LM to write the code in Python, I ask it to write in Daphne. And Daphne is a verification program language that can both do execution and verification at the same time. And ChatGPT actually have some logics of Daphne itself, and it can actually give us a really looks good code in Daphne with the insurer here. I don't know whether you can see it, but with the insurer here, and the insurer is a post condition to be verified for a code. So, and here we can see that the insurer just to ensure the max one is a max value in an array, in a set. And we can start to trust this kind of code as long as the verified property after the insurer is correct, the precondition is correct, and the verification pass definitely is checked. But this remains our future work. We're still working on that, and we have a paper submission to computer-aided verification. And to conclude, in this paper, we present the first benchmark for network orchestration and share our experience, and we automate the common workflow for LM-powered prototypes. We actually show that it's really potential to build some system and simplify the complex network orchestration task with LM. But there's remains some challenges, as mentioned, is on reliability and cost. And thank you for listening.
Thank you. Thank you. Yeah, I apologize for the delay problems. Mid-Echo is looking into it. We're not quite sure what it is. So there are some questions. And yeah, Rod, you're the first.
Hi, thanks. It was a really interesting talk. I learned quite a bit from it. In your work, you used several of your plots had accuracy as one of the things you're evaluating, and several of us were talking in the chat window while you were presenting about what the definition of accuracy is, which probably there's some underlying definition of whether or not it's actually met some requirement. But
yeah, I think in the translation from natural language input to the formal specification, we just consider accuracy as the percentage of the number of the percentage of the requirements that has been successfully translated into a formal specification. And
how do you judge that? How do you judge that it has been successfully
because
translated?
as in the experiments, we actually have a I don't know whether you remember the process. We first generate a few specifications based on the configuration. And this specification is already, we consider it as the ground truth. And then to get the natural language input, we actually convert the ground truth to a natural language input using some predefined templates. So we can, after translation from natural language back to the formal specification, we can compare the generated one and the ground truth itself.
Okay, thanks. By the way, I forgot to give my name. My name's Rod Van Meter. Sorry about that.
Will Earp, SWGFL. I just wanted to know, when you trained the small language models,
Yep.
How did you get the examples together? How many examples did you produce for it?
You mean the small models of I mentioned in the second task that it can never succeed.
Yeah.
First, we also tried the small models at that time, and the largest one among that smaller models is GPT. The largest one at that time is GPT 3.5. In the small model, we consider even it's not small enough. And we also actually for each experiment, for each task, we allow 10 attempts for LM to get to the correct goal. So I mean, by providing, for example, 10 times of feedback, if it can succeed, we can consider it's one successful run. And so we did it run by, I think, more than 50 times. So we actually, it can actually try attempts to generate the correct code by 10 times 50, which is 500 iteration with LM, and it can still fail in the generation.
I mean, when you fine-tuned the model, how many examples did you provide to it to fine-tune it?
Oh, we didn't try fine-tuning the code generation task. We only tried it in the translation from natural language to the formal specification.
Yeah, that's what I'm asking about.
Uh,
So you use QLoRa to train the model, right?
sorry, I didn't get it.
You use QLoRa
Yes, QLoRa.
to fine-tune the model.
Yes.
So how many examples did you provide?
It's like 300, yes.
Okay. I'm just thinking you might have had more success if you provide maybe 1,000 examples or.
I think the recommended number given by ChatGPT, GPT OpenAI itself is 300, but I need to double check that.
Yeah. Okay.
Hi, Cheng-Ji. My name is Dave Plonka. I'm with WhiskNet. The part about this that got me a little excited that I thought was tractable was taking natural language and turning it into a formal specification instead of writing, say, router configs directly or something. But the part following on to Rodney's question, there's all these reports in the presentation about saying 100% accuracy. And so, as you said to Rodney, you took a real configuration in the real world and generated the natural language from that. So how is that natural language? Because it's deterministic. If you take the formal specification and say in English, for instance, it must come out this way. In the example you showed here, that's not in the paper, you said the traffic needs to go from Rome through to Milan through a firewall. But then in the formal specification, there were 2 firewalls. So it got me thinking, there's not only one natural language thing that goes to one formal specification. If there were, then it would be easy to say it's 100% accurate. This turns into this turns back into this. But we have ostensibly an infinite number of natural language ways to say the requirement. And then I'm wondering how many things could it generate formally that your process would consider accurate, 100% accurate? Because you can have superfluous or extra configuration, right? So what do you think about that? Like, how do we go to the part where we say take any natural language, and then how many formal specifications capture what was said?
Actually, we have the concern about this when we do the experiments, because, for example, if I say network requirements, I want to direct traffic from A to B through a waypoint C. It's actually can mean both. It could be just be translated into one single requirements of the firewall of the waypoint, but it can also means that if I need to route the traffic from A to B through C, it also means A can reach B. So there is some ambiguity of the natural language itself, but we try to make this more clear in our system. So if you say waypoint, just say waypoint rather than with the reachability requirements. But we consider this as an important part actually of the ambiguity of the natural language, and also potentially some conflicts of the natural language, because the requirements itself may have some conflict. So if we put the conflict and ask LM to generate, it's likely to result in an even worse answer. So we also have a conflict detection at the beginning before the generation actually, but I didn't show it here, but I have something in the paper.
All right, thanks.
Chenju here. One quick question. What's the time cost for the evaluation or your demo? Is it faster than the conditional tools?
Sorry, you are asking the performance of?
Time cost. How faster is your value evaluation with LLM?
It's actually, I have to say, much slower for now, because in our demonstration, we have the experiments with GPT-4, and GPT-4 itself, we don't have it locally. We actually need to call the API of the from OpenAI company. So it means that we need to send a request to OpenAI, and then it will send us back the request. And who knows how many requests OpenAI will receive at the one point. So it really depends on the delay of itself. But if we try to run a local model, it should be faster. But the demonstration itself, it's like two minutes. And I think the whole running of the system, it takes like one minute like this. But it's slow, but we just want to show the feasibility for now.
Oh, thank you. Another quick question. Compared to the fine-tuning method with the foundation model, what's the advantage of prompt method like RAG and future learning, or in context or in learning?
Sorry, can you repeat that? I didn't get it.
In your presentation, you mentioned two methods. I remember one is for fine-tuning a specific model with
another one is pre-training. Yes.
Yeah.
And pre-training means that we first have a model with nothing, with no parameters, and we pre-train it. We train with different parameters from the beginning to the end, and it's actually super resource intensive. And usually, in our university, we don't train it because it takes time and also takes money and also takes GPU resources. But it's hard to say whether fine-tuning, whether pre-training will make it better than fine-tuning, because let's say fine-tuning, we take something already from a general purpose model which has been trained on something, some general purpose. But the general purpose may also include some necessary parts. For example, the understanding of natural language. We might need LM to understand the natural language itself and have some reasoning capability in itself. So if we take it from a general purpose model, it's already been trained on this task, but even not focused on this task, but it's already know something about this. But if we pre-train a model by ourselves using some specific data set, it might lose the capability of doing some general purpose stuff like reasoning. So if we put the same input, but just asking to fix the question, it might not even know how to do it because it loses the capability of reasoning by our data set. So I cannot say whether fine-tuning, I cannot guarantee that whether pre-training will be better than fine-tuning, but we have to try it just to know.
Okay, thank you.
Jérôme François, thank you for your talk. I think it's a bit of follow-up on what has been discussed before as well in regard the ambiguity in the natural languages and also on the different metrics that we use. I think one thing that you mentioned is that of course you have to build your own benchmarking data set for testing your different approaches. My question is also common. Do you think that because here you build your own, you take specifications and you go back to the natural language and then pre-translate? You discussed that before. Do you think somehow it will be better that rather than doing everything like that, that we could, like in other community, as a kind of community effort as well, to have, for example, data sets that we build and that we validate what is the expected outputs? You know, that for example, in image processing or whatever, they do like that. They have corpus and they try to have people that validate what should be the output. Because here, my understanding is that you have one expected output and then you use standard trick and compare how close you are to this expected output. But maybe there is outputs that are completely different, maybe on what you expect, but can maybe exactly perform the same task or in different way. Do you think that it would be good to go in more this type of, let's say, systematic approach to build, for example, data sets that we need for training, for testing in this type of work? Yeah,
I totally agree with that. Because even for, I actually have the same concern when I did the experiments, because getting a data set from like a reverse process is a bit not that convincing, I have to say. And also it's a bit, after the input is a bit unified, and even they have a similar pattern, which I don't know whether LM can actually learn from the unique pattern. And it's good to have a better data set. I totally agree with that.
Yeah, just to follow up on that, maybe just more common that thing in maybe more, let's say, classical tasks. For example, for general purpose model, you have things that most of people can understand and validate if it answer good or not.
Yeah.
In case of specific tasks like we are generating configuration of code, you need expert people. And I think this is why it's more difficult to have these big data sets
That's true.
compared to what we have.
Yep. Thanks.
Thank you.
Yeah, thanks everybody. So one question from my side. So what advice would you give to people who wanted to generate more, say, complex configurations, for example, let's say security policies or something where correctness is really crucial? Do you think that's could be a problem, or?
I think it's a really serious problem for now by doing, if we want to use ARM to generate some security stuff, because as I say, the answer generated by ARM could be either wrong or even malicious, and you never know. But so that's why we are actually working on a formal verification with ARM by ensure the 100% accuracy. I mean, by formal verification, we can ensure 100% accuracy, not accuracy, sorry, the correctness of the code. So, my experience of LM these days is that it can actually replace some daily, let's say, repetitive tasks. Like if I want to write an email, I can ask it to rephrase it, something like this. But if you want to really trust it to do something, it should still take extra time. And if you want to use LM to generate some networking, security stuff, it's always better to have to do it slowly, step by step, by simple tasks, simple steps, and also have people, let's say, trading the steps just to check whether the answer generated by LM is either correct or bad or not.
Okay, yeah, thank you very much, Dandy, again. Congratulations. And so I give you the ANRP reward.
Stopped.
Yeah, that's true. Okay, so that was very interesting. So we are moving on to the next talk, and the next prize winner, that is Henry Birch-Lee.
Hi, everyone. My name is Henry Birch-Lee from Princeton University. Today, I'm going to be presenting Tango, Secure Collaborative Route Control Across the Public Internet. This is work done at Princeton University with the wonderful researchers you see on screen here. Oh.
You should have control.
Is this on?
Should be. Is it on? It's off. Yeah, I don't know. Did you pass it control? Oh, it has control. Try again. Let's try again. No. Yeah, of course. So something is wrong with this computer. Okay, thank you. No.
So let me begin by asking the question, is today's internet good enough for performance critical applications? And the scenario I want to bring up is, imagine that we are a university and we want to work with a small cloud provider that, say, has the best price and capabilities for what we're trying to do. And our goal is to outsource performance critical apps that need to be reachable from the campus to this cloud provider. And the assumption is that us and the cloud provider will communicate over the public internet. Now, the problem is that the internet doesn't offer performance guarantees. So we can have latency between us and the cloud that is too high or inconsistent. We could have unacceptable levels of packet loss. And ultimately, the reliability of these performance critical apps suffer. So the good news is the networking market has found a solution to this. We simply have to pay hypervisors or network as a service people a bunch of money and our problem is solved. Specifically, two technologies that sort of aim to solve this are edge compute, which is putting performance critical apps close to or in edge networks, and then network as a service, which are on-demand sort of least point-to-point links between two sites. They often offer a higher reliability or higher throughput than the public internet alternative. The problem is that we feel this is somewhat anti-competitive, and it creates an environment where really only the large hypervisors can deploy these edge nodes all over the world. So this is an example of AWS and Google's edge network. As you can see, they have, dozens of points of presence all over the world to deliver fast content. This is not really practical from a smaller cloud provider. And then also these point-to-point links are quite expensive, and they're really only sort of an option by major enterprises. And you have another consideration that they may not be in more developing regions. There's only so many locations on that drop-down where you can actually lease one of these links. So what would it take for the internet, the public internet, largely developed by the IETF, to actually serve performance critical apps? And we postulate that it's really three things. We need to know what paths are available. So this is the path diversity problem. We need to be able to accurately measure the performance of those different paths. And then we need to have some type of dynamic route control to put traffic on the best path for our particular use case. So what we're proposing is tango on the internet. This is a picture of me and my spouse dancing tango. As you can see, it's a very tight collaborative dance. And we're proposing tango across the internet. So here, two edges on other sides of the internet collaborate closely to optimize edge-to-edge routing. So let me revisit those three problems from earlier and talk about how Tango solves them. First, looking at path diversity. Why is it hard? Well, the main thing with path diversity is that BGP, the de facto routing protocol on the internet, only exports a single path. So Edge 1 here only gets one path from its upstream AS5. Edge 2 kind of looks like it's in a similar, better position with two paths because it's multi-homed. But if you notice, there's actually a lot more paths to get through this topology, and Edge 2 can only choose whether it sends to AS2 or AS4. It can't influence anything in the core of the topology. So we want to do better than that. And what we have is an algorithm that we call BGP Pathfinder, which exposes path diversity in the core of the topology without any explicit support from these core backbone ASs. The way BGP Pathfinder works is that it has no knowledge of the internet topology, and it begins by making a unmodified standard BGP announcement from the receiving edge. And this propagates through the internet as usual. Here we have the green is the announcement propagating, and then the purple is where the return traffic would flow based on that announcement. So after receiving this announcement, the next step of the BGP Pathfinder algorithm is actually to suppress this announcement. So it uses a BGP community that blocks exporting of this announcement over a particular link, and that causes the internet to converge on another path. So in this manner, we actually just coaxed out another path from the core of the internet that we can use to reach the other destination. So once we find this new path, we start repeating this algorithm. So we go and block the new path. That exposes yet another path through the internet. And we repeat this process until every possible path we could find, any additional blocks essentially results in no path being found. So at this point, BGP Pathfinder has kind of exposed all the paths it's able to. And now that Tango knows about the different paths, we use a strategy of announcing the different paths with different IP prefixes. So the technique is, once finding the relevant BGP communities that expose each of these paths, the destination node enumerates different IP prefixes and attaches the different sets of communities to each announcement. These BGP announcements are stable, so they simply go out with the communities and they stay announced in that state. The source then can do dynamic routing by selecting which IP prefix it would like to send packets to to reach the destination. In this manner, we can keep the BGP announcements stable, but still get per packet granularity on routing decisions. So now that we have these paths, we actually have to measure how well they're doing on the internet. I want to begin by sort of introducing the concept and the general idea of wide area measurements and why there are some challenges. So imagine that we're making a forward routing decision, and that's essentially impacting the hops along this green path shown here. Well, the main tool for measuring network performance, at least in the latency space, is round trip time. And round trip time inherently has the reverse path baked in. So you can imagine that an issue on the reverse path is inseparable performance measurement wise from an issue on the forward path. The next thing is that round trip time requires the other endpoint to actually act your packet back, which means that whatever access network that's going through affects your round trip time. So this is modeling, say, a wireless link at the final access network. And now your interdomain path decision is being impacted by the variable quality of that last hop wireless link. And then finally, we're actually making an implicit assumption about the layer 4 protocol. When we're measuring round trip time, we are assuming that we have a protocol that's going to act back with a certain pattern, and we can correlate those acts. Right away, simple options like delayed ACK go in and impact this type of measurement. You can imagine more complex behavior or receiver buffer fills can impact these measurements. So if we are actually going to make a routing decision based on performance, we need to measure performance in a way that's robust against adversaries. Reason being that if an adversary can make her path look better, then we'll end up dumping all of our traffic along that path. And this is essentially a new form of BGP hijacking. So we need measurements that are also robust. And all of this has to run at line rate. So this might be a 100G link, and we need to measure all of that. Our approach to measurements is to use the collaboration between the two edges to attach a custom Hango header, which we add using either a programmable switch or eBPF. Because of this, the measurements only include the one-way wide area component of the network, and they do not rely at all on application behavior. So we're essentially measuring time from switch 1 to switch 2, not round trip time. We protect these measurements from adversaries to make sure that adversaries can't hijack the packet by protecting several key fields in the measurement packets. So we protect the sequence numbers, we protect the timestamps, and we also protect route control messages. So those are encrypted if we have to actually change a path. I'm going to talk a little bit about how we protect sequence numbers because I think this is quite non-intuitive. Timestamps, you can sort of use a less granular timestamp and just sort of sign at that granularity. Route control messages are only sent now and then. But sequence numbers, we have billions of packets going through these packet processors, and we need to protect every sequence number. So the way we do it is with what's called a book cipher. We essentially have a large, pseudo-random block of cryptographic material stored in the switch. And whenever a packet comes through, we index that block, and we pull a 1-bit signature from the cipher book. And then we attach that 1-bit signature to the packet. So I'm sure all of you who have studied some security know that a 1-bit signature is probably not your ideal signature length because an adversary now has a 50-50 chance of forging it. But keep in mind that for an adversary to meaningfully affect loss, particularly at the speed of, say, a 100 gigabit link, the adversary needs to guess a whole lot of signatures. So with every guess, the adversary has essentially a 50-50 chance of being caught. And as the adversary has to guess more, the probability they would successfully guess all those signatures to meaningfully impact the loss on their link goes down. So this decreases exponentially, meaning that for sort of any reasonable amount of performance tampering, we would actually get a detection with this 1-bit signature scheme. Finally, I want to talk a bit about the route control philosophy we use. So there's a kind of interesting problem in wide area route control, and that's that if you imagine here, edge 2 is sending to edge 1. Edge 1 gets to collect the one-way delay data, so it knows how well the paths are doing. But edge 2 is the one that's actually sending the outbound traffic, and edge 2 is the one that needs to know if it should change routes. So the kind of naive solution is you just dump data back from edge 1 to edge 2. This can consume a lot of bandwidth, particularly at high line rates or high data granularities. So what we do instead is that Edge 1 and 2 are collaborating. So Edge 1 is actually responsible for computing the route control decision that will be taken at Edge 2. So Edge 1 collects and stores all of the performance metrics locally. It decides if Edge 2 should change its sending route, and in the event that it wants to change Edge 2's route, it sends back a route control message asking Edge 2 to change. So I want to talk about our evaluation of the Tango system. First off, how many paths did we actually find with these BGP tricks? To measure this, we ran the BGP Pathfinder algorithm between 503 globally distributed node pairs from the cloud provider Vultr. It took about 30 minutes per pair using one IPv6 prefix. This can actually be parallelized if you have multiple prefixes assigned to each node pair. And by default, Vultr only gave us a single upstream path. What we found is that for 80% of the nodes, we were able to successfully find additional paths. In the median case, we're able to expose 3 paths. And for some nodes, we had as high as 10 to 12 different paths that we could use to reach the other node. So the next question is, now we found these paths, but maybe BGP was doing the right thing all along and it was perfect, you know? We wanted to find out if we could actually beat BGP by using these alternate paths we found. To do this, we took measurements from 25 global locations to 2 different destinations. We used Stockholm and Los Angeles as the destinations, and we took fine-grained measurements with loss and one-way delay every 10 milliseconds. What we found is that for many pairs, the path found by Tango had a 22% lower latency than the BGP default path. And in some extreme cases, we saw even up to a 39% latency improvement using Tango. So finally, I proposed this system of taking, secure measurements at line rate. And then the question is, can you actually fit this on a programmable switch that would be able to forward at, 100 G speed? So we implemented this on the Tofino 1 programmable switch. The signature values were sent to the switch in the data plane. So we essentially had a signature generation server that generated the cryptographic blocks and then dumped them into the data plane. We then recirculated packets in the Tofino 1 to write to the registers. And we were able to write 2 to the 20 signatures in 2.6 milliseconds, even when we had reasonable cross traffic that the switch had to process at the same time. And this was sufficient to keep up with 100 Gbps line rate. Because don't forget, we're only writing 1-bit signatures, for each packet. So I want to conclude by talking about 3 interesting things we found doing the Tango work. So first of all is that we actually can coax alternative paths out from the public internet. These paths often do have improved performance over the BGP default path, and we can run trustworthy telemetry at line rate in the data plane. So I really appreciate everyone's time, and I'd like to end by taking any questions.
Very nice, thank you. Okay, do you have questions? And please use the queue system.
Yes.
But go ahead while we wait.
Okay, so this is Yong Sui from Tsinghua University, and I think this is a very good work. I'm wondering if you have measured the difference between different paths you found. I mean, if we have 2 different paths, but if the path is very close or has a large distance between each other. So have you evaluated this distance? Thank you.
Are you talking about 2 paths that share a link, or?
Yes, right.
Yeah, so we do not account for whether or not paths share a link. Actually, in fact, every path shared at least 1 hop because it was sharing our upstream data center provider. We treat all the paths as distinct. In our measurements, we do find some paths have extremely close characteristics, but we simply look for the best path. In general, the system is robust against sort of enumeration of multiple paths that have the same performance characteristics.
Okay, thank you.
Hello, Bjorn from Domus. Just a question about the latency improvements. So you mentioned a percentage point improvement in latency. Is that the mean latency? And have you looked at like the stability or reliability, like the high percentile, 99 percentile latency, or other metrics like that?
Yes, so we did look at stability. So I guess there's two measures of stability. Like first, do these lower latency paths like have low jitter and high throughput and other sort of quality metrics? In general, they did track with good metrics. We also measured loss over the links and jitter as well. And then in sort of the performance improvement, I think the median point was about 10 to 15%. We noticed a significant number up at the 20% mark. So you should check our paper for the more accurate performance improvements. We did a path stability examination in the paper. We found for most of the paths we found, like these alternative paths were just as stable or more stable. We also looked into dynamic routing, so whether we could route around sort of unsavory network conditions that lasted for a short period of time. And, over the course, both the paths we found and the BGP paths would have these types of events, and we were able to route around them and show a performance improvement.
Cool, thanks.
Hi, my name is Alexander Azimov, Yango. So first of all, I admire your work, and it looks quite fun to measure the multiple paths that does exist in the internet this way. But I'm curious, have you considered operational consequences? Because as you described it, it requires a lot of cooperation between parties, especially transit ISPs. And they need to provide communities to make it work. And they also need to provide kind of transit control communities that will be passed through their networks. And more even important, they need to provide you a selective community so that will be blocking advertisements to their customers that they don't provide anyway. So what is the interest of ISPs to be part of this dance?
So as of today, many of the top backbone ISPs do provide such communities that allow you to selectively block to customers. All of these works were done, the measurements were in the real world with real ISP communities that we programmed into our system. I think the main incentive for ISPs is for miscellaneous traffic engineering, that it gives more fine-grained control to their customers. So in general, I think the what we call action community space has been stable, if not growing, in the sense that customers do use these for traffic engineering, and many ISPs have well-documented sets of communities. I think there's a more long-term question as to whether this type of manipulating core paths would be seen as unfavorable to core ISPs. I think in the long term, we think that market economics could play a role, and that ISPs with this system, ISPs that offer superior service will get more traffic. So hopefully it will reward sort of superior service and not just have everyone turn off the communities, which would have traffic engineering effects.
Just a comment that normally what ISPs are providing, yes, they do provide communities for their customers. They do not provide communities to block advertisements to their customers.
No. We assume they block, we use a realistic model, like these are all real communities. They block announcements to peers and transit providers on communities attached from customers. Yes. And that's enough to impact essentially the up-ramp route, and that gives you a lot of diversity in the internet. You can impact up-ramp and then which peering link you go over. You don't need full route. We don't prove that we expose every path in the topology. That's not the point of this routing protocol. It's just to get more paths out of what would previously have been one path.
Okay, thank you.
Hi, Robert Story, USC ISI. You just recently mentioned that you also looked at stability, and everybody knows BGP is dynamic route shift, can shift frequently. How often were you reevaluating the stability of the paths that you had found, or doing rediscovery, or is it a manual process, or are you monitoring to try and detect it?
So I think I think in the full system, if you were to deploy it over time, you would probably have to do this path rediscovery process maybe on a weekly or monthly basis. That's around the level of stability we found. If you take paths you found, say, a year ago, and then you rerun them, you do sometimes have path collapse where two paths that previously seemed to be distinct with BGP communities have converged, and then you have the flip side of maybe there's new paths because someone onboarded a new upstream and we don't know about it. So essentially, if you want to keep your paths as distinct as possible, you need to rerun this roughly on the order of when people are finding new upstreams. Now, I think there's another question of stability as like if there's a transient link up, down, does that impact the system? I think we're actually much more robust to that because if you imagine traditional BGP routing, when that link goes down, your packets will not reach the destination until BGP reconverges on another good idea. With Tango, you actually have those other paths already announced, already stable, and they're hot. So as soon as you notice a performance degradation, Tango hops over to another link that's not being affected by that transient effect. And then once the link, comes back up and your BGP paths re-stabilize, you can measure that path and realize, oh, it's good again, I want to go back there. So I would say we give superior performance in the case of sort of transient failures. And on the week to month scale, you should remeasure the paths to address the case of more fundamental topology changes.
Rod Van Meter, no longer ISI, sorry, the ICAO University. That was a long time ago. Where'd that come from? The questions about stability are good ones, but I'm also interested about scalability in multiple aspects. Did you measure the path length of the things you're looking at here, and does that have any influence? And then with 120,000 ASs and 1 million routes out there, what happens when everybody deploys this?
So I have an answer on both of those. I would say on the path length, it's typically quite stable compared to the BGP defaults. You can imagine like between these data centers, it's often up to transit provider A, across peering to transit provider B, and down at transit provider B. And if you imagine two data centers that both have 3 transit providers, we can select which upstream transit provider we want to use on the uplink. And then by controlling peering behavior, we can select which downstream transit provider. And all of these in this scenario are 2 hot paths. So we noticed that just by sort of enumerating this space of what would be considered equal-ish paths in BGP, matching on a local pref and path length, just by enumerating through the equal paths, we discover the vast majority of good paths. Now, when you get to that slide where I say some pairs have 10 to 12 paths, yeah, you start enumerating down at path, 4 or 5 AS paths, hops, and the original path might have been 3 or something. So then the scalability one is really interesting. I think the main thing to note is that 1, we're in IPv6, and 2, when you look at the IPv4 route table today, there's roughly 8-ish redundant prefixes to reach every ASN. So if you look at sort of unique ASN destinations versus how many announced prefixes there are, I think largely due to prefix allocation concerns, like AWS announces maybe 50 prefixes from the same data center the same way. So we think that if you were to solve those allocation issues, you could get a lot of route table space back to simply allow, in the neighborhood of 4 different paths for each destination. And IPv6, and then obviously these are all minimum /48, so you still have tons and tons of end host addressing that you can put at the end of that.
Thanks.
Rüdiger Volk, now retired, but a couple of years ago I was responsible for a large network and dealing with BGP policies and stuff like that. And I would like to note, you obviously are depending on transitive use of the communities, which is not actually something that is a given. Mm-hmm. And from my considerations of doing as good security as I could, actually there are good reasons to disallow your customers to send communities upstream further, because I, as the operator, am responsible for the signaling to my direct neighbors and kind of controlling what some distant downstream customer might want to fiddle there is kind of out of question. So kind of being very secure-minded there, the transitive communities don't work. There are very few networks that actually apply that kind of hygiene, but one should not be surprised to run into it.
Oh yeah, no, absolutely. There are networks that don't support transitive communities. So I would say there's still a substantial amount that do. There was a good IMC paper on this, a while back, and we see transitive communities propagate through the route collectors at a quite reasonable rate. If you do have a case of a network that doesn't apply transitive communities, you can still use this technique to impact one more hop than you would have otherwise by strictly, strictly doing neighbor selection. I mean, I think personally the really cool stuff comes when you can be 5-6 layers deep in the topology and select through that. But I understand there are security concerns with transitive communities.
Okay, great. Thanks very much, Henry, once again.
Thank you.
Okay, Ali, you can come on stage. So I cannot stop sharing again. Nobody can stop sharing. Okay. So here goes. Just say something about the queue. So we have another Meet Echo problem now. I cannot unshare the slides. There may be a permission problem. Oh, yes, the clicker. Yeah. You're right. Yes. Thank you, Beno. Okay. Okay, now we go. Yes, it's sure. Okay, sorry about that. Okay, Ali Nur, you have the floor.
Thank you very much, Dirk. Good morning. My name is Ali Rezaki. I'm co-chairing the Sustain PRG with my colleagues Yves Schuler and Michael Wetzel. We had our first Sustain session this Tuesday. I want to give you a bit of a glimpse of our charter and what we discussed in the first meeting, and hopefully bring this new proposed research group to your attention and solicit your participation. Sustain RG has the vision to contribute to the advancement of the internet, as of course all of IRTF research groups do, from the perspective of sustainability and being part of a sustainable future for our societies and the planet. And we want to achieve that through a collaborative research experience, which is multidisciplinary. For all purposes, there are different sustainability definitions. Of course, at the root of these definitions lies the UN definition from 1987, which you see on the screen. There is some translation to be done from this high-level definition, but nevertheless, it is a guiding, let's say, text for all of us, starting from the definition and then from the 2030 Sustainable Development Goals, and also these 3 pillars of sustainability. We want to keep them in our minds. Environmental is, of course, the emergency today, but we need to be aware of the social and economic perspectives as well. Now, why does it matter for IRTF or IETF or ICT community to engage on sustainability challenges? And of course, we are all part of the global emergency that we are going through, and that's the 1.5 degree threshold. Some say we have already irreversibly passed, but some say there are still, let's say, opportunities to avoid such an outcome. That's the high-level challenge. And accompanying that, we have the net zero targets from most of our organizations, and there are approaching targets of 50% reduction, 100% reduction, and ICT community plays a rather small role as compared to other sectors, it is often said, but not necessarily so. Everything matters here. It's a global effort, and when we look at the numbers, actually, the impact of the network is almost as strong as the data centers, and each can match the impact of a developed nation. So we want you to be aware of this impact, that it is not small, the impact of the network to the climate emergency. And of course, there are also the trends going forward. We are considering 10 years down the line, and by then, what will be the impact of AI or other emerging network expansions, notably in the mobile access, but also in the applications driven by networks. So when we put all this together, there is space that we should and we will try to innovate in to have sustainability outcomes. I'm quoting things from the charter. You can have a look. This is just to bring this to your attention. I will skip this and go straight to our ambition. So in IRTF, we want to create another research community focusing this time on the sustainability of networks. And when we say community, we want to generate a common vision, common set of questions, common set of understandings within IRTF and IETF around this topic. And we want to be focusing not on the standardization aspects like Green Working Group would do in IETF, but on the research, in-depth research that is backed by experiments. And first and foremost, our target is to develop the research questions, where we want to bring the academic and government research together with the implementers from companies, vendors, operators, and create this long-lasting exchange, both within IRTF, but also externally. So if I talk about our early focus, We want to first understand where we stand as a community, who else is working on this topic, and how can we exchange with them. And then we want to identify key owners for research that can come to our research group and work with us to develop these questions and answer some, in an innovative way, how can things be done better. So we are looking for the large gaps in our coverage of this topic. We are looking for the controversies. We are looking to understand these things. And we are looking for the biggest impact items. You will see going forward how we will try to build this community. We will create a group of reviewers. We will look for the champions. So it will hopefully benefit you to come to our research group and bring your early research results, get feedback from other researchers, but also companies who engage in IETF, so that the applicability of your research will be augmented. As a selection, you will again see in the charter a selection of our, a detailed representation of our research areas. Here I wanted to outline just a few. We will first look into characterization of the footprint before doing any attempts to improve on the sustainability impact of the networks. We want to first characterize this. This is a huge challenge. Where are the biggest bottlenecks? Where are the biggest impacts today in terms of energy, but also GHGs, materials? And we want to do this in a comprehensive way, while of course each of us would have their focus areas. We want to understand how these things evolve or interact and come about in a system, which is the network. And when we say, let's say, a system level impact, we want to do this in an interdisciplinary way as well. Not only, as we have seen, operational aspects have a key influence, of course, on the sustainability impact, but other sectors, other domains like policy have a huge impact. And life cycle is also a systems level consideration. When we develop new technology or innovations, we are focused what we achieve in that narrow scope. But when it comes to sustainability, you need to think of how you would build that system, how you would implement it in the field, how you would operate it, and how you would lead it through its end of life. That's the whole life cycle, and that's what counts. So we will focus on this. In our first meeting, Yuka Manner from Aalto University gave us a glimpse of what life cycle considerations are, and it was a very interesting discussion. Another area which is of course of great importance is the architecture, network architecture implications of or impact on sustainability outcomes. In the e-impact program, Yari and Suresh have been leading a study group on this, and we are looking at the research gaps in that area, which we want to carry forward into this research. You can read about this mode of operation. Of course, we want to meet during the IETFs, but we also want to develop workshops along major networking conferences. We want to create this focus on ANRW, which I'm quite happy this year. We worked with the program committee and included these sustainability topics on energy, of course, but also characterization. on the internet footprint, and I'm hopeful we will receive some good papers and start moving in that direction. So I encourage you to engage with us. Here is the mailing list, which is not very active at the moment, but I'm hopeful it will pick up soon. And you can reach us, chairs, and find out about the new RG in the data tracker. Any questions, comments, you're welcome. Thank you.
Thanks, Ali. Yeah, so this is interesting because it takes like whole systems perspective. And so if you're interested in that topic, please subscribe to the mail list and keep discussing with the community. Thanks, Ali.
Thanks. Thanks also to Colin and Dirk in their support of launching this new research group. Looking forward to. Thank you very much.
Right. Thank you, Ali. I have one more important thing. Rod, do you have a question? Oh.
Yeah, just on that, Dave and I were chatting as you were starting. Your initial title slide said sustain PRG as in proposed research group. Isn't it now a full RG or am I?
No, it's
We're still proposed.
It was first launched in January, so it will be proposed research group.
We are still in probation period.
Okay, good. Thanks.
Yep.
Okay, thanks. Okay, I have one more really important thing. Maybe I need to get up for this. Okay, thanks again to the prize winners and to Ali for their presentation. I wanted to take the opportunity to thank Colin once again for his great work and his many achievements for the IRTF. So on behalf of the IETF and the Secretariat, I'd like to give you a little gift, and that should be useful with the time that you gained now after finishing this job. Thank you very much again. Okay, and yeah, and with that, we can close the meeting. Thanks for coming. See you next time.